China has just done what no nation has ever achieved, bringing back the first rock samples from the moon's far side. And what's inside them? The oldest volcanic rocks ever found, sitting next to volcanic materials so young, it shouldn't even exist there. This single discovery rips apart everything we thought we knew about the moon's history, forcing scientists to rewrite billions of years of geology. Let's dive straight into what Chang'e 6 found, and why it's blowing the minds of planetary scientists worldwide. The Chang'e 6 mission wasn't just another step in lunar exploration. It was a leap that no one saw coming. For decades, scientists thought they understood the moon's far side. The theory was simple. It cooled quickly after its formation. Volcanic activity fizzled out billions of years ago, and nothing significant happened there since. That theory? Gone. When Chang'e 6 touched down in the Apollo Basin within the South Pole, Aitken region, and returned its precious cargo, scientists were stunned. Inside were two kinds of volcanic basalt that told a completely different story. The first type dates back an incredible 4.203 plus or minus 0.004 billion years, the oldest lunar volcanic rock samples ever brought to Earth by any mission. These formed not long after the moon's crust solidified from a global ocean of molten rock, making them a direct chemical fingerprint of the moon's earliest geological activity. But here's the real twist. Alongside these ancient relics, Chang'e 6 carried rocks just 2.807 plus or minus 0.003 billion years old, some of the youngest volcanic material ever found on the moon's far side. That's a staggering 1.4 billion year gap in volcanic activity. It means this supposedly dead hemisphere stayed geologically alive far longer than anyone dared to guess. How is that even possible? Normally, volcanic activity needs heat. On the moon, that heat mostly comes from KREP elements, potassium, rare earth elements, and phosphorus, which trap thermal energy in the crust. But here's the kicker. The far side is notoriously poor in KREP. Without it, standard models say the magma engines should have shut down billions of years earlier. And yet, here we are, young lava on a cold, KREP-poor surface. The explanation? Still unknown. Maybe a hidden heat source deep within. Maybe a more complex mantle evolution than current theories allow. These rocks are more than samples. They're time capsules. They're rewriting the moon's geological script, proving that the far side was still active long after the near side went silent. And they raise a bigger question. If volcanic activity could survive there against all odds, what else is hiding beneath that ancient surface? The age of these rocks is shocking enough, but their chemistry tells an even stranger story. When scientists analyzed the Chang'e 6 samples from the Apollo Basin, they found something missing: KREP elements. On the near side of the moon, KREP is common, acting like a cosmic heat blanket that keeps volcanic activity alive. But on the far side, almost none, just trace amounts. That's like finding a roaring campfire in the middle of a snowstorm, with no wood to burn. And it doesn't stop there. The water content in these basalts is unbelievably low, between 1 and 1.5 micrograms per gram. For comparison, near-side volcanic rocks can have up to 200 μg/g. That's over 100 times drier. Why would the far side be so parched? One leading theory points to a cataclysm more than 4 billion years ago, the colossal South Pole Aitken impact. This was one of the largest hits in solar system history, so big it reshaped the moon's crust and possibly blasted away heat-producing and volatile-rich materials from the far side's mantle. If that's true, the mantle beneath the Apollo Basin has been running on empty for most of lunar history, making the existence of young volcanism there even more baffling. But there's another twist. Paleomagnetic studies on some of the 2.8 billion year old basalts revealed something incredible: a magnetic field signature. This means that when these rocks cooled, the moon's core was still generating a magnetic field, long after scientists thought it had shut down. This late magnetic pulse doesn't fit the old models. Something must have stirred the lunar core again, perhaps giant impacts reigniting convection, or localized mantle plumes unleashing heat from deep inside. The takeaway? The far side of the moon isn't just the quiet side. It's a survivor, shaped by massive impacts, stripped of resources, yet somehow managing to spark volcanic life and even a magnetic heartbeat long after it should have gone cold. And that leads us to an even bigger shift. These samples are forcing scientists to rewrite the moon's entire geological timeline. These rocks don't just tell us what happened, they help us figure out when it happened. Until now, most of our lunar timeline came from the near side. Scientists would count the number of craters on a surface and compare it to known sample ages. But that method had a flaw. It assumed the far side's crater history matched the near side's. The Chang'e 6 samples have finally given us a direct calibration point for the far side. Here's how it works. The 2.807 billion year old basalt provides a precise timestamp for a specific surface. Scientists compare the crater count there to other far side regions, creating a far more accurate age scale. This is huge, not just for the moon, but for dating surfaces on other cratered worlds like Mercury and Mars. The ancient 4.203 billion year old basalt plays another role. It anchors the early lunar timeline, showing exactly when the crust stabilized after the moon's violent birth and during the late heavy bombardment, a period when the solar system was still a shooting gallery of giant impacts. Then there's the magnetic puzzle. Those 2.8 billion year old rocks should have cooled in silence, but instead, they captured whispers of a still-living magnetic field. That means the moon's core, once thought to have gone solid long before, was still capable of generating a dynamo. Why? Some scientists suspect that giant basin-forming impacts acted like defibrillators, jolting the core into short-lived bursts of activity. Others think deep mantle plumes might have been releasing heat in isolated hotspots, keeping parts of the dynamo alive. This combination of precise dating, magnetic surprises, and crater calibration is a rare jackpot in planetary science. In one mission, Chang'e 6 has sharpened our dating tools, challenged our thermal models, and revealed the moon's inner engine might have been sputtering long after we thought it died. And if that much can come from a single landing site, just imagine the chaos in our models when we start sampling other far-side locations. Chang'e 6 didn't just bring home moon rocks, it cracked open a vault of secrets we didn't know existed. In its cargo, proof that volcanic activity on the far side spanned 1.4 billion years, rocks drier and poorer in heat-producing elements than anyone imagined, and traces of a magnetic field thought long gone. It's redrawn our lunar map and sharpened our clocks for dating the solar system. But here's the real question. If one mission from one location can rewrite the moon's history this much, what's still waiting beneath the untouched craters, mountains, and deep subsurface? The moon is no longer a frozen relic. It's an evolving archive of planetary secrets, and we've only just begun to read its pages. Thanks for watching. If these discoveries fascinate you as much as they do me, make sure to like, share, and subscribe. The next chapter in lunar exploration is coming, and you won't want to miss it.